Yep, it's pretty cool. Okay, hi everyone. Um, so this is the Casper Weekly stand up. Uh, I have a couple of updates. I think Nate has a couple of updates. So it's gonna be a pretty short, relatively pretty short one right now, because not many, because Greg is on honeymoon and Vitalik, I don't know. I I think he's traveling right now. Um, anyway, so last week I think I talked about validator rotation. And I was able to do validator rotation and prove that that was like safe with respect to the fork choice rule. Um, this week I kind of worked a little bit on this, on having it be kind of safe for someone to make a block even though they haven't previously bonded with respect to the fork choice rule. So I'm not necessarily saying that that's easy to make safe economically, but with respect to the fork choice rule, you can kind of have a notion of like balances and weights where your kind of weight gets added as soon as you make a protocol message. And that's like safe with respect to the fork choice rule. Um,
Sorry. So does that mean that you essentially bond just by creating a block for the first time somewhere?
yeah, exactly. Yeah. It basically has to. It's basically like you know how I have the blocks be able to specify new weight functions, and that's kind of fine.
Sure.
I can also have blocks do that and be created by a validator who wasn't in the weights function of the previous blocks.
Well, that's pretty cool.
Yeah, and I can just like prove in the normal way that that's safe with respect to the fork choice rule by showing that like it's deterministic uh, in the view of a node, and that it is possible for it to be safe. I.e., like there are states, protocol states, where the estimates won't change.
So follow-up question: what's the benefit of doing that as compared to just having them send a bonding transaction?
I think I think it's potentially good for defending the system and for picking it up if ever all the validators go offline, but it's just an exercise for me in seeing if the extent to which it's easy for me to change the fork choice rule and still or like add validator rotation rules and kind of make like give myself like the ability to explore this like this design space safely with respect to the fork choice rule. You know,
Cool.
uh,
Yeah, sure.
even though it might not be what we end up going with, because if there might be other safety concerns, then just that the fork choice rule is like well defined and is like meaningfully useful for a consensus protocol.
Cool.
So I thought that was pretty cool. Yeah, so that's my main like Casper Research update. I started thinking a little bit about liveness strategies, but not so much like giving explicit liveness strategies, but just trying to think about models for timeouts and basically a distributed strategy to make a certain message propagation order happen. Um, it's kind of interesting. I'm mostly using uh, basically, I'm getting them to try to get a certain digraph to happen in terms of the message passing. And I'm thinking about kind of uh, I mean, like basically, if I have synchronized clocks, it's quite easy to give a strategy for when to try to do it. If I have synchronized clocks and a bound on message propagation, and then I'm just trying to see like how I can be more flexible and like start from there and kind of like relax my assumptions.
Cool.
Because like if I could just make a DEG, I mean I can make a blockchain. I basically like have like uh you know ideally this the thing I like is basically like basically you have a blockchain with like a certain orphan rate that's targeted so that it takes a certain number of heights to finalize. and then like if you want to finalize right away, then you get something that's more like a round-based or success protocol. If you're willing to like, if you want to have much higher message overhead, then you do like this round robin blockchain.
Why does targeting an orphan rate give you a consistent?
Well, so I mean, I guess the right thing, the correct way to put it is like maybe we target the time to finality, and then we get and then we minimize the orphan rate as a result. But because like imagine you want to finalize everything ASAP, then you have to do like 2 rounds of messages that are kind of concurrent, and in like these 2 rounds. So like everyone sees what everyone's initially input, and then everyone sees that kind of a commitment from everyone that they've seen it, and then you're kind of done. And that 2-phase thing is going to orphan most of those blocks, right? Only like 2 of those blocks are going to be in the longest chain.
Sure.
And so if you want to finalize things real quick, you have to orphan a lot of blocks.
Oh, cool. Yeah. Okay.
Yeah, it's kind of cool.
Yeah, I get you.
Hey, I've got a question. I was just going to lurk, but how does proof of stake deal with the problem of transactions that far outweigh the value of the stakes?
I mean, transaction finality, I mean, is the whole point of having like actual consensus, and from the point of view of like finality and like decisions on the level of like the state of the protocol or like the state of the consensus. Because basically like it's only really a problem with respect to liveness, not so much safety. Because once you have safety to a certain threshold, people will just like subjectively never revert due to like the kind of, because they make like a decision.
No, I'm talking about, say you've got a set of validators and their total stake is $1 million, but someone wants to.
Yeah, it's fine. So what I'm saying is like after it gets finalized, everyone is just gonna everyone's gonna just refuse to revert no matter how like what you do later.
No, I'm not talking about later. I'm talking about as soon as they see the thing, they decide, hey, I'm going to steal this. And they abandon their stake in order to get the money transferred to their account rather than.
No, I don't think that can really happen, right? I mean, so like, only there's like a notion of like validity of transactions and blocks that stakeholders have to, like be in line with, or else like no one will accept their services, right? And they're limited to only valid transactions with valid blocks. So that's like one big thing. And so their only real freedom is either to like include or not to include, to like get consensus with safety or not. So the worst they can do is not process the transaction. Is what I'm saying.
There's no way they could substitute some other.
No way. There's no way. No, they're not. They don't determine the rules of the protocol, right? All they do is form consensus. They don't actually like determine validity of messages. So like, they can't really just take the money. There's like rules about like what state transitions are valid.
So even if the entire network together is colluding on this,
basically like it's a mistake to think between I think of the nodes that form consensus as like the entire network though. There's like full nodes, there's service providers, there's users, right? Everyone who's running a node according to the protocol is going to just not know about blocks and messages that are invalid. In like one model. The other model is that they like notice them, drop tiers, like penalize validators, that kind of thing.
It's a bit like the DAO hard fork, right? Some invalid state transition as compared to like the old protocol, and some people, went with it. And so kind of, all of Ethereum colluded, except for the people who didn't and stayed on Ethereum Classic, right?
Yeah, so that's an interesting one. Yeah. So but that represents a change to the protocol as opposed to some people acting within the protocol and taking strategies that are definable in the protocol. So there's no like kind of so the one way to think about it is in terms of what is like if I'm running a node that runs the protocol, what are the things that you can send it to change its state or to change its view of the blockchain, or it's fork choice rule. Maybe is the best way to think about it. And the answer is well, I mean, it's never going to accept any forks with invalid blocks. So you're only going to be able to show it forks with valid blocks. If it detects equivocation, it's going to assign the weights of the validators to 0. There's certain constraints, that of what you can show a node in order to change what it thinks the canonical order of events is. And so you can kind of look at blockchain security through the lens of what it takes to change your node's choice of fork.
Cool. All right, awesome. Vlad, if you're done your stuff, I can go.
Yeah, go ahead. I'm excited for your update.
Cool. So the theme for the week was find the bugs and write the tests. I guess is what I was officially calling the week. To kind of I mentioned last week there was that kind of weird bug that was very rare where we were kind of finalizing 2 inconflicting blocks, and I spent a while trying to get to the bottom of that, and it turned out to be ultimately very uninteresting and just a typo somewhere. But in the process, I found another bug or 2 that I've since fixed. But kind of, this has made me even more paranoid and even more convinced that we need to get some legit testing going and stuff. And so I've started down the road of unit tests, integration tests, etc. Yeah, so that's kind of the main part of my update. There's one more interesting bit, which is that kind of I've been thinking about, so we do this calculation, right, where we make a graph and there's edges between the nodes, which each node represents a validator. If those 3 conditions we keep bringing up, which is they've seen the latest block from each other, that's on the candidate estimate, and they'll never be able to see another block anywhere else.
And their own latest block is on it.
Yeah, right. I guess that actually in condition
maybe
2.
That right. In the second one that you gave now, the third one that normally.
Yeah, that's what I was thinking.
Yeah, that's actually true. Yeah, so maybe those 2 conditions are enough.
Yeah, and
but it's good algorithmically to check this condition of whether they have a latest estimate first.
Sure. Yeah.
Because if they don't, then you can immediately drop. If they do, you can immediately drop them.
Yeah.
Sorry, if they don't, you can easily drop them.
Yeah. But anyway, so I've been thinking about we kind of so we have this graph, right, and then we kind of do a search through the graph for the highest weight clique, and we're using a library to do that currently, and it's not really slow, at least on the order we're doing it, because there's only 5 validators. But once we get up to 1,000 validators, it's probably going to become pretty intensive.
What's the most you've tried though?
100.
With the safety detecting?
Yes.
And hey, it's not that slow?
It's not so great, but it's usable, but it's not particularly usable, I guess is the way I'll describe it.
Yeah. But do you calculate it once every time that there's a display, or do all the nodes calculate it, or how many times are we reading this thing?
Yeah, I have all nodes calculated every time they receive a new block.
Okay, so that is a lot of stuff, that a lot more than you would be doing if you were just running one node.
Yeah, no, yeah, that's fair. But even then,
so it's not necessarily that bad, right?
It's not necessarily awful. It'd probably be good to get some hard numbers on it and stuff.
Yeah, it'd be cool to run a test net and see what you can run when each node is only responsible for their own node.
Yeah. How manageable is it?
Because when you're running lots of nodes in Python, it's I think we
yeah,
run into it is going to be some constant factor slower.
Yeah, sure. But anyways, so kind of one interesting thing that's just kind of worth mentioning because it's kind of cool is that we can. So here's what we can do. We can find that first thing we do is we find the edges. So we find all the edges between all the validators, and then we add the edges to the graph and then look for the max weight clique. But what I realized we could do instead is kind of just look at the number of edges we have and then kind of use that to make a decision about what's the minimum size of a clique that must exist somewhere, right? So you can kind of say like, oh, let's say there's 5 validators. If there's, I don't know, I can't do the math in my head right now. 10 messages, I guess. So 10 edges. So an edge between every pair. It's an undirected graph. Then we can kind of say, oh, everyone kind of must be connected to each other, and we must have a clique of size 5, right? And so if we just look at the number of messages, we can kind of make a guesstimate about what the minimum size of the clique must be, which like kind of makes things like hyper efficient, which is kind of cool.
But you also have to say like, okay, and we have to assume that it's the smallest weight nodes that have that clique.
Yeah, exactly. So you find the minimum size, and then you just pull off the smallest nodes, or the smallest node, the nodes with the smallest weight,
and you add their weight, and you're like, okay, we have at least this much fault tolerance.
Yep.
Or exactly. two times this minus 100%.
Yep, exactly.
Yeah, so I think that's really cool because it's super efficient. Is it it's gonna be interesting to see how practical it is.
Yeah. Yeah. I mean, when running it, it doesn't look, I mean, this is not a great like metric, but when running it and looking at it, it doesn't look like that much of a lower bound.
You mean that much of a lower bound?
Yes. Yeah.
Yeah. That's cool. I'm excited to see people using all sorts of different oracles. And that's one of the things I really like about this whole protocol is that it's like really flexible with respect to safety dissection and making decisions, because like the core of it is really just this fork choice rule mechanic.
Yeah. Super cool.
Yeah, I'm also super excited to do the concurrent virtual machine replication, or the concurrent, or like rather than replicate a block, blockchain, we could replicate a rewrite proof system. It's kind of my. I mean, I'm excited to like do that next, I guess, because I feel, I guess, at least on the consensus front, I feel like with validated rotation stuff, if I can really like see what the limits are there, then I think that we'll be pretty much mostly ready to like incentivize it and like not really look back at decisions in terms of the consensus protocol and how it works. Especially if we have like a whole quiver of safety oracles.
That's super exciting.
There's also the liveness thing, of course, which is actually another little area of research that needs to be done before the consensus stuff is done. But the liveness thing is, I think that this like simple parameterization is really like the right kind of thing to think about. I even would be comfortable looking at something like having the validators produce blocks in a Poisson process, and if they're honest, they try to build it they just like commit to having seen as much stuff as they actually have seen in their dissertation, and as long, and then everyone could just produce blocks out a Poisson process, and we can tweak it to do to decide on the finality rate and overhead trade-off. Because we have really low overhead if we just do like a block every 10 minutes. But that's not really, we don't necessarily want to maximize throughput at the cost of latency to that extent. We might want pretty fast finality and pretty fast blocks. So I think it's totally reasonable to have like a few seconds. We can even have a few seconds of block, and ideally, like I would have the thing that we kind of want is just have like a liveness strategy where there's just like a parameter for targeting the latency. And I think there's like kind of two latencies that matter. One of them is like latency to finality, and the other is like how long you have to wait until your first confirmation. Those are the ones that I really kind of care about. just at first thought. So yeah, so I'm excited about that. And then after, if we have like a parameter and we decide, okay, look, we want like 4-second blocks and finality in X long, and we can have like have a live strategy for that, and then incentivize it. I think we're pretty much set. Incentivizing safety is incredibly easy, right?
Yep. Don't equivocate.
Yeah, and if you do, you lose all your money. Yeah, but this liveness is way harder, right? Because like there's the non-attributable nature of the faults.
Yeah. So quick question. So you said something earlier in the week that I've been thinking about, and I'm not sure I fully understand. So I just want to clarify. So you said you're not so comfortable with reducing the weight of offline validators. Which seems so like if someone doesn't make any protocol messages, kind of that isn't a problem.
Well, so of course it's a problem, but well, I mean, so I guess there's basically, with respect to the fork choice rule, like there's a certain kind of logic to how the validators weights change, and the more that you change validators weights, the like less efficient the protocol is, because you the way that you sync up requires that you can't really jump heights as much. So imagine if between like height like 1 and 100, the validator set didn't change, and the validator set like finalized a block at height 100, you could just like jump to that block. You get to like inherit all of the, you wouldn't have to check finality at every height from 1 to 100 if the weights never changed.
Sure.
So if the weights are always changing, because just like as over time, like at every block height, then you have to sync up really from the last finalized block, and one height at a time, which maybe isn't that bad, but like that's why I don't like changing the heights really all the time. And there's also a kind of we're gonna need to have either timestamps or like certain or block heights, and I prefer timestamps. And timestamps is something that I haven't really added into the protocol with respect for like, at least for the safety stuff. In liveness, we might want to have that, but basically, I think it's just a little. I think that my hesitation is just that it's more complicated with respect to fork choice, and because basically the fork choice needs to encode, or the blocks in the fork need to encode the weight changes, because otherwise we don't get to have our asynchronous safety proof.
Sure. Yeah. Okay.
We really want to have this asynchronously safe kind of. We want to have. I definitely don't want to lose the safety proof, right? I don't want to make any protocol changes that means that we no longer benefit from the kind of estimate safety consensus safety proof.
Gotcha. Cool. Thanks.
But so I think it can be done, but basically it has to be done with weight changes given in blocks, and we need to understand that the more we change the weights, the less skipping we can do in the fork choice rule. And basically, like the thing I want to avoid, and I guess that's one of the reasons why I'm interested in this thing for validators to make new blocks, just based on having like a balance in the pre-block, is basically because I don't want to have to. I want to have it be kind of like an objective thing, as opposed to having it be just a matter of, like something that like nodes might disagree about, right? I want node state to be like entirely determined by the messages they've received. I don't want to think about when they receive them. With like, definitely exceptions, like one exception, which is kind of like the subjectivity thing, which is like, the decisions that your node makes and never reverts on. But with respect to the fork choice rule, I think everything should work in that deterministic way before finality.
All right, cool. I think I followed 95% of that. So
I mean, I don't think I was super coherent, so I will give it if you have like a question or something.
So you don't want node state to be totally determined by messages. That's the bit I did not follow.
You do. The only exception is decisions.
Ah, I see. Okay, I get you now. All right.
So like,
Cool.
imagine if you set your node's decision threshold to like 110% fault tolerance, then it would never make decisions. It would always kind of follow the fork choice rule.
Yeah, I get you.
But at that point, it would kind of basically be doomed to start from the genesis block forever.
Yeah.
And that doesn't work because of this kind of weak subjectivity concern about like the long range attacks and stuff like that.
Yeah. Oh, interesting. Cool.
And so we have to make decisions in order for the protocol to kind of always be only driven by current deposits, right? Because you need to have like a recent deposits only in any forks that you possibly choose.
Mm-hmm.
And that means that like you need to make decisions, and decisions are the only thing that don't have this property that the node state is determined by the protocol message they receive independent of the order they receive them.
Yeah, gotcha. Okay, cool.
Yeah. Cool. Yeah. I mean, it's really interesting, and I really like, the fork choice part of it. I think the fact that fork choice rules are not dependent on the order of message arrival is like, and the fact that they're useful for consensus at the same time is a super interesting thing, because like, it sounds like a commutative data structure in some way because the message arrival order doesn't matter, but the thing we get out at the end is like a total order that we can kind of end up being stable on, assuming some fault tolerance threshold isn't violated.
All right, so I have a quick question for you. So one of the bugs I fixed this week was that we kind of had ties at some point. So validators just because of how weight was selected, were ending up with the same weight. And so
totally need tie breaking.
Yeah, right. But so kind of the one interesting thing is I was kind of thinking to myself, oh, as of now, because there's this bit in the fork choice that kind of randomly selects one of the blocks if it's not the same weight. It doesn't. It doesn't necessarily have to do, because it's a random choice, right? It doesn't necessarily have to do with message arrival order, but it also means that nodes might choose a different estimate with the same view. And so I don't think we were actually satisfying.
Yeah, well, exactly. And so but there's a way that, I mean, it's pretty. You just have to refactor slightly. I mean, I normally just like gloss over because like I know it can be done, but basically like, and I have done it, and it's like kind of like just a little. I mean, basically instead of thinking about the estimator as a function that returns a singleton, it's a set function, and everyone has the same estimate. Means really everyone has the same return value for their estimator, which is going to be a singleton set if you have like kind of no ties. When you do have a tie, then you have multiple things in the set, and you do have the same thing, right? It just and then you kind of make we think of the non-deterministic choice just as something that is kind of not really their estimate, but just something they choose for their message.
Okay, I got you. Yeah, I fixed. Anyways, I fixed
in that set. Will satisfy for the validity of messages.
Okay, yeah, I get you.
And I think that's fine. I think basically like, there's no like existential problems to do with this like edge case. And basically there's two cases where ties can happen even if we insist on tie breaking property, right? Empty views and views with 100% Byzantine faults.
Okay.
Right.
Yeah, sure. So you're not really justifying with anything, essentially.
No, in empty view, but in the other view, you're justifying with only like latest messages from Byzantine validators, and therefore
right, which is
nothing to go with.
Yeah, yeah. Okay, sure.
Cool. Yeah, and so it's totally interesting to try to like be totally precise about all the definitions and stuff. And I'm excited to take another stab at formal verification with Yoichi after Metropolis stuff. try to get this proof at a high level, be formally verified, in like Isabel or something.
Awesome.
Yeah, it's gonna be cool. What's on your timeline? I guess we should just focus on getting stuff done before DEF CON.
Yeah. I'd like to have like my one real goal, I guess, is like just to get some legit tests on this thing.
Right.
But,
are you nervous?
Yeah, I'm a bit nervous.
Are you nervous about bugs or about the theory being wrong?
Not so much about the theory being wrong. A bit about bugs.
Nice.
Yeah.
Flattered.
Nice.
All right. Sweet. Yeah. I mean, I'm not too worried about the theory. I think I'm pretty happy about the theory. But once there's formal verification, I will be even happier because like it'll force me to look at like all of the like gory details.
Yeah, it's great.
Mm-hmm. All right. Well, I think we're pretty much done then. Do you have anything else?
Nope. We're good.
Cool. Mike? Nothing?
See you later.
Great. See you guys next week.
See you guys. Thanks.